Hello, students. It is my pleasure to see you all today. So today we'll be solving IGCSE past questions on the topic called motion. So stay tuned as we'll be solving some questions together. So let me open the document. So do not forget to subscribe to the YouTube channel, Physics for Everybody. The subject is physics and the topic is motion. And this class is meant for students in year 9 and year 10. So I'll put up my video so that we can focus on what we have to do today. Good. Now let's go. So, okay, this is just my biography. I teach WIAC, NECO, IGCSE curriculum. So, and we're talking on graphs. We're focusing on graphs of motion. We talk about the distance time graph. I also talk about the velocity time graph, okay? Where the vertical axis shows the velocity and the horizontal axis shows the time. And then that's it. Let's go straight into some questions. So we're solving real life examples, like the examples of a car that has a parachute attached to it. And you know the parachute will reduce the speed of the car. Let's go straight into solving the question. IGCSE past questions on motion. Question number 1. A large stone, initially at rest, falls from the top of a building. The stone takes 3.2 seconds to fall to the ground. For this stone, air resistance can be ignored. Stating the formula that you use, show that the speed of the stone when it hits the ground is 32 meters per second. The first thing you have to do is what? You have to state the formula you use, okay? Yes. That's the first thing you do. Stating the formula that you use. And what formula is that? We use V equals to U plus GT. Why did I say G? You know, the equation of motion, the first equation of motion states that V equals to U plus AT. But because the stone is falling downwards, okay, it falls from the top of a building. It is falling downwards under the influence of gravitational field strength of the Earth. So if something is falling under the influence of gravity, acceleration in that case will be equal to G. So you know that the first equation states that V is equal to U plus AT. So instead of having A as our acceleration, we will replace our acceleration with the gravitational field strength of the Earth. Okay, that's why our formula is V equals to U plus GT. So let me remove A here and put G here. So that's it, V equals to U plus GT. That is the formula you use, stating the formula you use. Now, the second thing we do is to show that the speed of the stone when it hits the ground is 32 meters per second. Well, how do you show that the speed will be 32 meters per second? We use the same formula, V equals to U plus GT. What is V? V is what we are looking for, okay? What is U? U is our initial velocity. The question states a large stone initially at rest. When something is initially at rest, it means that the initial velocity is 0 meters per second. What's our time? The time taken is 32 seconds. Okay, the stone takes 32 seconds to fall to the ground. So our time is 32 seconds. What else do you need? You need the G. You know, our U is 0, which you have written. Our time T is 32 seconds, which you have written. What about G? The value of G is 10 meters per second square. That's the gravitational field strength of the Earth, 10 meters per second square. Now let's substitute those values into the equation for the final velocity. Okay, good. For the final velocity or final speed, you have to show that the speed of the stone when it hits the ground is 30 meters per second. So what's the speed? Our final speed V equals to U, which is 0. You know this equation we are using, U plus GT. Our U is 0, right? Good. Our G is 10, and our times T is what? Our times T is 3.2 seconds. Now let's substitute those values into the equation. V equals to 0, which is our U, plus G is 10, multiplied by T, our T is 3.2. 3.2. This simply means V equals to 0 plus 10 multiplied by 3.2, you get 32. And that automatically means V is 32 meters per second. And that's what the question requires of you. It says that you should show that the speed of the stone when it hits the ground is 32 meters per second. And that is what you have done here. Let's go to the next question. On figure 1.1, let me reduce the font size so that the question can be clearly seen. All right, let's go. Okay, let me do this further. Okay. On figure 1.1, draw the speed time graph for the fall of the stone. Label with an alphabet X the line on the graph. Okay, so what would the distance time graph of the stone look like? You know, the stone takes 3.2 seconds. It takes 3.2 seconds to attain a speed of 32 meters per second. Yeah, our calculation shows that the time taken is 32 seconds. You see, our time here is 32 seconds. Let me use the pen to write on this. Our time is 32 seconds, okay? And within 32 seconds, it attained what speed? It attains a speed of 32 meters per second, which we got after solving. So we are going to plot our graph such that it will take 32 seconds for the car to attain a speed of 32 meters per second. It's clear, right? Good. So our graph must be plotted such that it will take 32 seconds for the car to attain a speed of 32 meters per second. Let me remove all of this so that we can focus on what we are working on. Okay, so let's get back to it. So you just mark 30 seconds. This is 0. This 32 meters per second. 20, 30, 31, 32. So this mark shows 32. Then it takes 3.2 seconds. 1, 2, 3. 3.1, 3.2. So we ensure that we trace 3.2 seconds upwards with a straight dotted line. You have to use your ruler so that you can get a perfectly straight line. My line has not been straight. Let me try my best to make it straight. Let's go. So I want to draw a perfectly straight line. So you use your pencil and your ruler to trace 3.2 seconds. And you trace it to the speed of 32 meters per second. You know, it took 3.2 seconds to attain a speed of 32 meters per second. Yes. So when you use your ruler to trace 3.2 seconds, and then you trace 32 meters per second, wherever they meet, that is the point where your ruler good. So your slope must pass through this point. Where this dotted line on 32 meters per second, where it meets the dotted line on 3.2 seconds. At this point here, so you draw a straight line from the origin, that's from 0, you draw a straight line to hit this point where those two straight lines meet. So I will do that. Okay, so I will draw a straight line from here, and the straight line was, so you must use your ruler to ensure you have a perfectly straight line. So that's it. That's what the question requires of you, okay? Label with alphabet X the line on the graph. This is the line, and I label it with alphabet X. Good. So the question says, draw the speed time graph for the fall of the stone. This is the speed time graph of the fall of the stone. Let us see the next question. Use the graph in II to determine the height of the building. When you talk of the height of the building, what does it mean? What does this mean? A large stone initially at rest falls from the top of a building. So when you talk of the height of the building, we are referring to the total distance traveled. Yes, the total distance traveled by the stone as it falls is given by the height. It represents the height of the building. Now, how do you find the total distance traveled by the stone? We find the area of this right angle triangle. Okay, that is the area under the curve. And what shape is this? The shape here is a triangle. This is a right angle triangle. So you just calculate the area of this triangle, that's all. Okay, so the distance traveled, which represents the height of the building, is what? Half base times height. Okay, which is the area of the triangle. What's the base? The base goes from 0 to 3.2. So our base is 3.2. Okay, and our height is the vertical distance from the graph. Okay, what's the height of this triangle? The height of this triangle is 32. Yeah, 32. You know, the height represents the speed in meters per second. Though we don't have to put this SI units. Okay, and the base is the time in second, 3.2 seconds. We also don't have to put this unit, SI units. So we just calculate the area of this triangle. That gives us the distance covered. Okay, good. So let me wipe this off so you can go and solve it on the space provided on the answer booklets. All right, so let's go straight into that. So your height or the distance is half base times height, and that is equal to half times your base is 3.2. Your base is 3.2, and the height is 32. And that will give you 102.4 multiplied by half. Okay, if you multiply these two, you get 102.4, and we still have to multiply it by half. Okay, that half in front of it. So half of 102.4 gives us 51.2 meters, and that's the height of the building, 51.2 meters. The next question says, a smaller stone than the stone in A falls from the same building. The stone is affected by air resistance. What happens to the air resistance as the stone falls? Underline your choice of answer. Okay. What happens to air resistance as the stone falls? You know, when an object falls under the influence of gravity, that object will be affected by drag. When an object falls under the influence of gravity, there will be a force of drag on it, or we call that force air resistance. And as that object continues to fall under the influence of gravity, air resistance continues to increase. It keeps increasing until the air resistance is equal to the force that is pulling that object downwards. Okay, so when air resistance is equal to the force pulling the object downwards, then that object stops accelerating, but keeps moving with a constant speed, and that constant speed is called the terminal velocity of the object. That's it. On figure 1.1, draw a possible speed time graph for the fall of this stone. Label with a Y, this line on the graph. Okay, so a smaller stone that is influenced by drag, what happens? The stone will not accelerate at a uniform rate, unlike this one. You can see that the acceleration here is uniform acceleration, right? Good. So in the case of that stone, there won't be uniform acceleration. Sorry. In the case of that stone, there won't be uniform acceleration. The stone will be affected by drag. I mistakenly cleaned up the slope of the first one, so let me put it back. In the case of the first, in the case of the first stone, the speed time graph is a straight line that passes through the origin. I didn't get a perfectly straight line. Let me draw that again. So in the case of the first stone, the speed time graph is a perfectly straight line from the origin and passes through that point where the speed of 32 meters per second meets the time 3.2 seconds. Now, as for the stone that is influenced by drag, the speed of that stone initially, the speed of that stone will begin to decrease and decrease and decrease and decrease further until the stone attains a uniform speed, which is called the terminal velocity. So this is what the graph of that stone that is affected by gravity, that is affected by drag would look like. This is the curve, and we label it with alphabet Y, just as the question requires of us. You have to label it with alphabet Y. Okay? Label it with the Y, and that's it. The second question says, figure 1.1 shows a distance time graph for a moving object. Describe the speed of the object between points A and B. Okay, between points A and B, what do you have? This distance, this is time, okay? You can see the slope. It's curved in a clockwise direction to the right-hand side. It curves in a clockwise direction. So the way the slope curves, it shows whether the object is accelerating or the object is decelerating. So if the speed time graph, if the distance time graph, it curves this way, it shows that the object is decelerating. If the distance time graph, it curves in an anti-clockwise direction, it shows that that object is accelerating. Now, in this case, the speed time graph from A to B, it curves in a clockwise direction. What does that show you? It shows that the object is decelerating. So describe what is the question request for? Describe the speed of the object. Okay, so if something is decelerating, the speed continues to reduce. The speed is reducing. What about between C and D? What about between B and C? What happens? Look at the graph. From B to C, what do you have here? From B to C, we have a straight line. Yes, if you look at the graph, you see that from B to C is a straight line. And what does that mean? That means uniform acceleration from B to C. So you come to this place and you say, since uniform acceleration, then we say the speed increases at the uniform rate. Okay? Okay, the speed increases at a uniform rate. Okay? And if you want to talk about the acceleration, you say the acceleration is constant. State whether the acceleration of the object is 0, negative, or positive, as shown on the graph. Between A and B. So if you look at the graph, between A and B, you can see that since the curve is to the right, is clockwise, then you say that the object is decelerating, right? Good. So if something is decelerating, what do you say about the acceleration? It means the acceleration is negative. So between A and B, the acceleration is negative. Why do you say the acceleration is negative? Because it is decelerating. What about between B and C? What do you say about the acceleration? Between B and C, the acceleration is positive because of the direction of the curve of the slope. If the line was straight and in this direction, then we say the acceleration is negative, okay? Sorry, this is not correct. This is not correct. This is for a velocity time graph, not for a distance time graph. As for a distance time graph, if you have acceleration, the curve would go, it will be curved in an anti-clockwise direction. That's acceleration. And if you have a deceleration, it will be curved, the slope will be curved in a clockwise direction, just like from A to B. That shows deceleration, okay? Good. So let's get back to it. So from B to C, where we have a perfectly straight line, what does that show us? It shows us positive, it shows us zero acceleration rather. So when the distance time graph is a perfectly straight line, that shows that the velocity is constant, okay? Or you say speed is constant. And whenever speed is constant, it simply means acceleration is zero. Yes, that means the object is not accelerating, okay? The object is not accelerating, or you say the object is traveling at a constant speed. Let's see. So the acceleration is zero. Our acceleration is zero. It's clear, right? Good. Why is our acceleration zero? Our acceleration is zero because the object is traveling at a uniform speed, and that is shown by the straight line. Calculate the average speed of these objects during the 40 seconds. What formula for speed? Speed is equals to change in distance, okay, divided by change in time, or you say distance divided by time. Take note that the time is 40 seconds. Let's go and pick our distance within 40 seconds. Okay, the time is from 0 to 40, okay? So within 40 seconds, what's the distance traveled? The distance traveled is 50 meters. So you come here and you put your distance as 50 meters divided by time. Your time is 40 seconds. 50 divided by 40. If you divide 50 by 40, you get 1.25. 1.25, let's see. 25, 12.5, yeah. 1.25 meters. So that is the speed, 1.25. I say the SI unit of speed is meters per second. So you state it there, 1.25 meters per second. What else do you have? Okay, I think that's good enough. Let's proceed. Okay, so let's proceed. Number 3, parachutes are used to slow down a certain racing car. Figure 1.1 shows the racing car of total mass of 750 kilograms, slowing down by using parachutes. Now this is the car. Figure 1.2 is the speed time graph for 20 seconds after the car reaches full speed. This is the full time graph for 20 seconds after the car reaches full speed. Okay, let's see. As time T equals to 6 seconds, the parachute opens. On figure 1.2, mark a point labeled A where the car is moving at constant speed. Now, if you look at the graph, when do we say the car is moving at constant speed? The car is moving at constant speed on this part where we have a horizontal line. Yes, that shows that the speed is constant, okay? When they have a curve like this, it shows that the speed is constant, okay? When the curve looks like this, it shows that the object is accelerating. When the curve looks like this, it shows that the object is decelerating. For instance, this part that curves downward shows that it's decelerating at a constant rate. That's why we have a perfectly straight line. And whenever you have a curve like this, it means it is decelerating at it means the deceleration is not constant. Okay. It means the deceleration is not constant. Yes. So let me clean up all these lines so I can mark the points where we have uniform speed. So the question says, so you mark a point labeled A where the car is moving at a constant speed. Okay, also we mark with B where the car is decelerating at a uniform rate. This is where we have constant speed, A. Okay, anywhere from here to this place, we have constant speed. And when it's decelerating at constant rate, this is where it's decelerating at constant rate because you have a perfectly straight line. Okay, it is from this place here, from here, where we start having curves, that we say it is decelerating at a non-uniform rate. Okay, but from here, wherever you have straight lines, it's just that we cannot determine whether this part is completely straight or not. Okay, but from this point here up to this place, you can see that we have a perfectly straight line. So deceleration is uniform within that region. So we mark the region where you have uniform deceleration, and we also mark the points where you have uniform speed, okay, or zero acceleration or zero deceleration. That's what I mean by uniform speed. So mark a point labeled C where the car is decelerating at a non-uniform rate. When do you have a non-uniform deceleration? This curve here. So whenever you have this curve here, you know that your deceleration is non-uniform. Okay, so you can mark it alphabet C. That's it. What else? Calculate the deceleration of the car as time t equals to 6.5 seconds. Now you go back and check. At 6.5 seconds, what do you have? You know, these 6 seconds. Okay. From the graph, this 6 seconds, this 7 seconds, okay? So it's very likely 6.5 seconds is around here. Yeah, it's very likely 6.5 seconds is around here. So how do you get 6.5 seconds? You know, you cannot specifically get 6.5 seconds, but we know very well that the acceleration is uniform from this point where I'm putting this blue line, blue mark, to around this point here. Yes, the acceleration is uniform within that region. We are very sure the acceleration is uniform within this region, as shown by the graph. So we can try to calculate the acceleration within this region. Whichever value we get for acceleration is the same thing as the acceleration at 6.5 seconds. Why? Because 6.5 seconds is within the time frame I'm picking here. So the time we have here should be 7.8. Yeah, this should be 7.8 seconds. That's the time we have. That's the time frame we have down here. This should be like 7.8 seconds. Okay, then what about our speed? Let us check what speed we have here. Okay, so our speed here is 26 meters per second. That's the speed we have here. If you try to count, this is 20, 22, 24, 26, 28, 30. Okay, yeah, so this is 26. Okay, this is the beginning of deceleration. We also have to pick the time from the beginning of deceleration. What is the time frame before the car began to decelerate? So we have that as 6 seconds, right? Good. Now let us solve deceleration. You know, deceleration equals to u minus v divided by t. In this case, our u is the initial velocity, which is 70. Our v is the final velocity after deceleration, which is 26, divided by our time is the time frame from 6 to 7.8. And that gives us 7.8 minus 6. That will be the time frame, 7.8 minus 6. 70 minus 26 gives us 44. 7.8 minus 6 gives us 1.2. If you divide 44 by 1.2, what will you get? Whichever answer you get, you put it down there as your answer. Let me just check this. 44 divided by 1.2. Let's see the answer we get here. 44 divided by 1.2 give us 36.67. So that is going to be the deceleration. 36.67. 0.67 meters per second squared. So you put the correct answer as well as the correct SI units. And that is what you have here. No. Our time is not 1.2. Our time is 1.8. Yes, sorry, I made a mistake. Let me clean this off. So the denominator here, which is our time is 1.8. So our time is 1.8. 7.8 minus 6 will give you 1.8. So 44 divided by 1.8 will give you 24.44. Okay, 24.44 meters per second squared, because it's deceleration. So the SI unit is meters per second squared. Let us check if there's another question we need to solve. Yeah, so all of this calculation should be here. Okay, good. So our deceleration should be solved here. Okay. So you're supposed to put we're supposed to put this deceleration, the calculation here, U minus V over T, and that is 70 minus 26 over 7.8 minus 6. And that will give you 44 divided by 1.8. What else do you have here? The resultant force. What's the formula for calculating force? Force is equals to mass multiplied by acceleration. Now we have to get the mass, okay? You know, we've gotten the acceleration as 24.44. Let us get the mass. What's the mass? The question says parachutes are used to slow down a certain car. In figure 1.1, shows a racing car of total mass 750 kilograms. So now we have the mass as 750 kilograms. And that's what we're going to use here. Okay? So our mass is 750 multiplied by our acceleration. Our acceleration is minus 24.44 meters per second squared. Okay, why? Because acceleration is negative of deceleration. You know, deceleration is 24.44. That simply means acceleration is minus 24.44. Since we are calculating resultant, the direction does not matter. What matters is the magnitude. So that minus is not of any significant importance. So just multiply 750 by 24.44. You get 18,330 Newton. That's it. That negative sign is not of any significant importance. Okay, the question C says, explain why there is no resultant force acting on the car at time t equals to 4 seconds. Now you go back to the graph and check what is happening at 4 seconds. At 4 seconds, what's the speed? We go to 4 seconds and we trace it upwards. Please ensure you use ruler to do this on your answer booklet, because it must have perfectly straight line. At 4 seconds, you have the line, the slope being completely horizontal. What does that mean? There is no acceleration. Okay? Yes, okay. When you have uniform speed, that means there's no acceleration. And our uniform speed is 70 meters per second. So when you have uniform speed, it means acceleration is 0. Okay, so explain why there's no resultant speed. Why there's no resultant force, rather. Why? Because the acceleration is 0 meters per second squared. Since your resultant force equals to mass times acceleration, hence our force is equal to 0. Okay, so when acceleration is 0, by the time you multiply mass by 0, you get 0. Hence, the resultant force is 0. This brings us to the end of these questions on motion. We will solve question number 4 till the last question in the next video. Thank you for watching. Do have a nice day. Ensure you watch the other video. Goodbye.